You are?
Yes, I am.
Okay. Okay.
Okay.
Thank you
So
very
good
much. Yeah,
afternoon,
please go ahead.
Anatoly. How are you?
I'm doing good, great.
Good to see you
And I
again.
hope everybody is doing great as well.
Okay,
Uh,
wonderful.
yeah, thank you for giving me this opportunity to speak.
Thank
And
you for,
uh,
for participating. Yeah.
yes, and today I'd like to talk about network optimization with annual logistics, and then about master planning. And I prepared several simple scenarios to demonstrate, and I'd like to say that they are kind of toy examples for easier understanding on the fly, because real life examples are usually too complex to demonstrate and to understand without spending a lot of time for analysis of the results. So these will be toy examples, but it gives us opportunity to understand what happens pretty quickly. So let me start. What is network optimization? When we talk about optimizing supply chains, we consider all possible options that are available within our supply chain. For example, different facilities that we can utilize, suppliers, factories, warehouses or distribution centers, and also possible flows between them. Different flows may appear between same sites because of different modes of transport or different batches and so on. And of course, when we consider all these options, we also consider corresponding parameters and constraints. Usually, these are different costs, like carrying cost, facility opening cost, fixed costs, and so on. And if we talk about transportation, it's usually cost of delivery. It may be also cost of production or supply cost. So all different types of costs that you can have in your supply chain. And when we talk about constraints, they can be pretty straightforward, like constraint on a throughput between two facilities connected to amount of vehicles available, for example. It may be production power, it may be capacity of warehouse, and so on. So the goal of optimization is to find an optimal solution for our supply chain. And usually when we say so, we mean best network configuration. The facilities that should be included in the supply chain and amounts of flows between them depending on the transport. And if we talk about goals, the usual or straightforward goal of optimization is profit maximization. And profit is actually revenue minus all the costs or expenses. And at the same time, this optimal solution should maintain all the constraints that we have in our initial problem definition. So as a result, we get optimal network structure with selected facilities and corresponding flows amounts. And of course, as a result, we can analyze different outputs, individual flows amounts, production processes, we can analyze different costs in this optimal solution, and so on. And Logistics provides all this data after optimization. Again, a bit talking about objective and the information required or available for optimization. As I already said, straightforward goal is to maximize profit, although it's not the only option, because sometimes you do not consider revenue at all and your goal is to minimize cost. It may be even more sophisticated. For example, you can set a constraint on let's say profit, that it shouldn't be below a certain level, but optimize CO2 emission. So in this case, optimizer will maintain this profit level, but the CO2 emission will be as low as possible. Of course, when we talk about network optimization, it's not a one-to-one correspondence to real-life supply chain. We use certain simplifications, and actually they are the following. We deal with flows and not individual shipments. So when you consider transportation from let's say a warehouse to a customer, you cannot track individual shipments, and you know only flow amount of products transferred from distribution center to customer. But you cannot say for sure, or you cannot distinguish between sending the whole amount in the beginning of the period or at the end of the period, or somehow uniformly distributed within the period. You know only one number, flow amount. But internally, we consider that flows are uniform across a period, although it might be not true in real life, because it depends on inventory policies and demand shape. Let me switch to Logistics. Here is the user interface of Logistics, and this is a tool which is designed exactly for optimization of supply chains and for analysis of their performance in time. And therefore, we have several experiment or types of experiments in Logistics. Some of them are analytical, specifically greenfield analysis and network optimization. And we also have simulation for dynamic simulation of supply chain, which allows us to understand how the system behaves in time. And in case of simulation, we can pay attention to individual events happening in our system, like individual orders or shipments. But we will talk about simulation next time. And today we'll concentrate on analytical method, network optimization. Here is the example that I've prepared, and we'll consider Brazil, and let's assume our company is supplying our customers with 3 types of products for restaurants: glasses, cups, and plates. There are some data defined in this scenario, like demand, facilities expenses for storages, transportation cost between suppliers and distribution centers, and distribution centers and customers. We have also processing costs. We have production cost in this case, because we consider not external suppliers, but probably some factories. And it makes sense if we want, or if we need to define additional constraints like throughput or production power. And in this case, we consider only trucks for delivery. If we talk about facilities, we have 3 distribution centers which supply our customers, and we want to find proper or best suppliers for each type of products. So you can see that inclusion type for distribution centers is include, and that means that optimizer cannot include or cannot exclude these facilities from the result, from the solution. But it has certain flexibility in selecting suppliers, because we have consider option defined in this table. So let me run the experiment. When I run the experiment, the data that we have in these tables is transformed to a so-called mixed integer programming problem, which is solved by internal solver IBM Simplex, which is included in any logistics. And here is the result. We can see that we have 1, 2, 3, 4, 5, 6, 7, 8 suppliers supplying all our distribution centers, which in turn supply customers. So 9, and if we or 8, yes, 8. So all the suppliers are included in the result, because based on the transportation transportation cost, it appears that all of the suppliers make sense for us. if we do like that, we'll see that these suppliers supply this distribution center. That one supplies both. These two supply Eastern distribution center, and these three suppliers supply distribution center to this south. So this is the baseline scenario. Let's assume that we act as a manager in our company, and we've got several opportunities to improve our network. Let's consider them one by one. The first opportunity is to contract another supplier, which is here, new tableware supplier, and it can supply cups and plates, and the cost, production cost for cup, for example, is lower than for the ones that we used previously, and the same is for plate. So result should be pretty obvious, but let's check it. I will run network optimization for this scenario again. And we'll notice that, yes, several previous suppliers were excluded from the optimal solution because that one is cheaper. So it replaces initial suppliers for plates and cups, for all the distribution centers, and supply is cheaper. Obvious result, right? And again, if we take a look on the map, we'll see that this supplier starts to supply all 3 DCs with cups and plates. The second opportunity that we have is another supplier located here, which can produce glass, and in this case its cost is the same as for south glass supplier, and these two facilities produce glass a bit, the cost of production is a bit higher than for northern and eastern glass supplier. So let's check. Oh, I'm sorry. Yes, this supplier is located to the south, but it also can ship directly to customers, but there is a limitation. It can deliver only within 300 kilometers distance directly to customers. So let's check whether it makes sense for us to consider this supplier in our supply chain. So we see that compared to baseline scenario, indeed, it makes sense to replace existing glass supplier with the new one, because it will not only ship to distribution center, but also it will ship glass directly to end customers. And let's take a look on the profit. So in the baseline scenario, profit is the following, like 10 million 335, and in this case it's 10 million 600,000. So it's definitely better than the baseline scenario. Let's consider the third opportunity, which is a bit more complicated, but let me explain this. So this is a discount supplier, and that means that this supplier can provide a discount based on the amount of product being purchased. And there's no discount if we buy less than 1,000. If we buy, it's 10% discount, sorry. And if we buy from 1,000 to 10,000, then it's 30% discount. And if we buy more than 10,000, it's 60% discount. So let's run this scenario. We see that profit is even higher. And if we check our structure, we will see that plate suppliers are excluded, and this one new plate supplier replaces them for all of the distribution centers, which is quite obvious, because the more we buy, the higher discount we get. We can see that in total we bought 6 million pieces, which is higher than 10,000. So it's definitely maximum discount rate, and that's why it becomes cheaper to deal with this supplier only, rather than individual suppliers to the south or northeast. So the discount rate becomes, or discount itself becomes more important than the difference in transportation cost. please, somebody let me know if you hear me and I'm not alone speaking.
Yes, Anatoly, we can hear you.
Okay, great. Thank you. So, do you have any questions on that part?
Is there any question for Anatoly?
I think Thomas has a question, yeah?
Yes, thank you. So this is very impressive with all these calculations there. I have two questions. The first is about the criteria. You bring in here only the price and reduce cost, but sometimes we have other criteria, how we choose a supplier, for example, lead time or the relationship or whatever. Is there a way to put this into your program or show it there somehow also?
Yes, thank you. Thank you for the question. So, as I already told, the objective function consists of objective members, and by default, it's revenue, like total revenue, minus all the costs that you have. It can be adjusted, so you can switch on and off different objective members, and you can also modify your objective members. So in this case, the discount that I was talking about is a part of supply cost, but we distract supply cost from revenue, but we add a discount as additional value that we get for buying more than certain amount. So this one is adjustable, but if we talk about other criteria, it really depends on what you are looking for. For example, if we talk about lead time, we cannot put that to criteria, but we can use a constraint for lead time. For example, this line represents flows from suppliers to distribution centers. And if we go to details, we can see that you can specify time limit. And in this case, the flow that exceeds certain transportation time will not performed against the same criteria defined in objective function. Did I answer your question?
Yes, thank you. I have another question. The question is about capacity. So we have to look at the demand by the customers and therefore from the individual distribution centers. Maybe a supplier does not have the capacity, so in addition we need another supplier.
Yes, we will talk about that later.
Okay. All right.
Okay. Yeah. Thank you for your questions. So probably I'm going faster than I initially
thought I would. But still, once again, we considered a baseline scenario, and we considered 3 options to how we can improve our supply chain. Cheaper tableware supplier, this one, a supplier with direct shipping to customers within 300 kilometers range. And we also considered a supplier that provides a discount based on the flow amount. And each of these options actually gives us better result. So if we take a look on each result, we also have this new supplier in our solution, and it usually replaces some other suppliers, which is quite obvious because the parameters of these suppliers are obviously better than of suppliers that we previously had. Let's do the following. Let's check whether it makes sense to apply all these opportunities that improve our supply chain individually, all together. The intuitive answer for a human would be yes, of course. If each of those improves our supply chain, then it definitely makes sense to to change our network corresponding to that, right? Adding all these 3 suppliers and removing the ones that they replace. But let's check our intuition first. So this scenario incorporates all the changes. So it has new tableware supplier, which is cheaper, new plate supplier, production. New glass supplier that can deliver directly to customers within a certain range, and new plate supplier, which provides these discounts. So again, I switch to network experiment and run optimization for this scenario with all the suppliers. Surprisingly, if I take a look on the structure of the result, we will notice that optimizer proposes not to use new tableware supplier. Of course, some of the new ones replace existing for Northeast supplier for plates, South plate supplier, and South glass supplier. But also the new tableware supplier, which was introduced here, is also not included in the resulting solution. and we've got only 2 new suppliers. That solution is a bit counterintuitive, right? Because each separate change improves our supply chain, but altogether, picture is different if we apply that altogether. And actually, that happens again because of new plate supplier, which makes sense to use in case of large amount of products being purchased, because we get maximum discount. And the benefit of using this opportunity is higher than the cheaper supplier introduced in the as the first step. Any questions or comments on that part? Okay, then I still have some time, and let me give some overview on the results that you can get from the optimization. So when you get a result, first of all, you can see the structure of your supply chain, both on map and on a structure view, which sometimes gives better insight on what happens. And also you get all available numbers from the solution. And these are actually product flows. And this table shows each individual flow that you have in your solution, with all the costs being applied or connected with that flow. Vehicle types being used, distances, and total flow cost. Site state is a table that informs you which facilities are closed or opened, or which facilities change their state in order to get a solution. In this case, you can see that all the suppliers or all factories are initially closed, and optimizer considers whether it makes sense to open this facility to use in supply chain. And that's why in this site state table, we see that initially closed facilities become open. That table shows other costs implied for certain facilities. That is the different view on 2 previous tables, status of the facility and the cost. That is the storage by product. So it's a table related to warehouses and distribution centers and factories, and it shows incoming flows of products and outgoing flows. And in case we need to store something, it will also show storage for a certain period. And again, if we have any storage costs, then we'll see it in this table as well. Production cost shows cost of production for different products on different facilities. And this table shows how much product or how many products were produced. And in case we have BOMs, bills of materials, defined in our scenario, which stand for raw materials. Let me show you this. Yes, we can define a bill of materials for a certain product, and we can define components needed to produce certain product. You can select products and quantity needed to produce that quantity of end product. In this case, the production flows will also show how many raw materials were consumed to produce certain amount of end product. Demand fulfillment table shows whether our demand is satisfied or not. In our case, we see that the whole demand is satisfied for 100%. Vehicle flows is a table that is utilized when we have full truckload shipments, and therefore we pay for utilizing a vehicle rather than for a flow. And again, different views on objective members, values, and overall stats for a solution. Another thing worth to be mentioned is penalties. You saw that we have this column in many tables, penalties. In this scenario, it's 0 because we do not have constraints that lead to penalties. But the idea is the following. When we put a constraint, for example, from certain distribution center to customers on max throughput, for example, that will mean that no customer can get more than 100 units of any product from this facility. And that means it is a hard constraint. It cannot be violated by optimizer. And if demand is higher and it is also a hard constraint, then our problem will not have a solution and it will be infeasible, and optimizer will tell us so. The problem is infeasible. I don't know whether it will work with this scenario, but let me try. I will remove penalties for demand. I will apply this throughput constraint. Like this for certain facilities, and I will run experiment again. You see, optimizer says that scenario is infeasible. It happens because we have two or several contradictory constraints. And optimizer has to maintain all of them. And simply we just do not have a solution. But if we specify a penalty, a constraint, for example, for a demand, the constraint for demand will become a soft constraint. That means that optimizer tries to maintain this constraint, but if this constraint is violated, then we pay additional penalty for violating that. It is called soft constraint. Let's run scenario again. And we see that now we have a solution. Although our profit is way far below zero. And if we go to demand fulfillment table, we'll notice that our hard constraint for flows is maintained, but as a result, we get low demand fulfillment percentage from 4% to 75 and 0.75, and that means that we pay additionally 5,000 per each not delivered unit. And you can see the penalties that we have to pay. And that's why our profit goes down significantly. Any questions?
Yes, Anatoly, I think we have a question.
Sure, please.
Yes, please. May Touch from Thailand. Over to you.
Hi, this is Metash from Thailand. First of all, thanks for your amazing demo and calculations. I have two questions. So the first one is that the demo that you show to us, we assume that we know the exact location of each DC distribution center and factory. Is it possible to run the optimization to find where is the best location for locating the DC as well? That is my first question. And the second question is that in some cases, the DC cannot directly reach to the customers. In some cases, the first DC may need to deliver to the second DC. We call it cross-docking, and the second DC will send to the customers. My second question is that, is your simulation support the cross-docking model? Thank you.
Yes, thank you. Let me Let me answer the second question first. So yes, this functionality is supported, and usually you define that using product flows table. So here you can see that we have the following definitions. Suppliers can ship to distribution centers, and distribution centers can ship to customers. But in case a distribution center cannot ship directly to some customers, it also makes sense. So probably here we will have not all the customers. Then it makes sense to add the following line. Distribution centers can ship to other distribution centers. And in that case, optimizer will automatically find a path through a DC in case there is no direct shipment to a customer. And regarding the initial locations for warehouses, there is another type of analytical scenario, which is greenfield analysis. And this experiment allows you to find optimal, not locations, but areas where your warehouses could be located. So let me select Brazil. Okay, I will create a simple example. So here is Brazil with the demand corresponding to population of cities. And this experiment allows you to find optimal locations for desired number of sites or distribution centers. So if I put 5 here, for example, it will give a result like this. So what happens in this case? Experiment considers as the crow fly distances. It doesn't know anything about surface, and in some cases a warehouse could appear in the river or even in the ocean or on top of the mountain. So it's a very basic experiment that clusters your demand points and finds so-called center of gravity based on flow cost estimation, which is actually amount multiplied by distance. And of course, it doesn't give you exact locations where to put your distribution centers, because it's a mathematically correct answer, but it doesn't consider real life constraints. But at least it gives you an area where your distribution center could be located. And then you can find different options based on your insights on availability of facilities in this area, availability of labor, and so on. But also, we have GFA with roads experiment, which is a bit more sophisticated. And for each found location, it also finds cities nearby with the minimum population defined here and chooses the best location from these cities based on not as the crow flies distance, but based on the road distances. So let me run this experiment again. And you see that now Logistics started to download distances needed to calculate the solution. It will take some time, but as a result, we will get not mathematically correct points from center of gravity experiment, but we'll get proposed solution where warehouses are located in cities or towns with the population not less than 15,000, as I put in the experiment properties. Usually, when we talk about real-life applications, in any case, the person who is solving the problem, who is selecting or choosing best supply chain structure, have to deal with other parameters like facility cost in certain place, labor cost, different constraints for throughput and capacity, and usually a person gives options to the optimizer. So, by the way, we've got a result. And we see that in this case, each facility is located in the city. São Paulo, Recife, and other places I cannot even read. So this experiment provided us more real-life applicable solution. Rather than this one, although results look similar, but the actual location is a bit different, because in this case it's exactly in certain city like Manaus. Well, here it's the same, but sometimes result really differs. Did I answer your question?
Yeah, it's very amazing. And it's very clear. Thank you.
Okay, thank you very much. And I think I don't know, Giuseppe, do we have time for this session? If yes, I'm ready to answer more questions if we have any.
Okay, Anatoly, I think the answer is yes, and there is and I think we have another question in the chat here from Bertha at UGM, I believe. Yeah.
Oh, Bob, I think we have two questions, one from Krishna and one from Bertha.
Yeah, let me read them. I found them.
Okay, I think the one from Krishna was more aimed at this morning's presentation here, but we can ask both and see if Anatoly can help. But let's start with Bertha. Bertha, you want to go ahead?
Yeah, thank you, Bob. Hello, Anatoly. Thank you for inspiring presentations. So considering that any logistic have a capability to solve the large scale problem and also involve some special aspect in the results, I think it's more interesting for the user. So that's why I'm thinking that would it be possible to use any logistic as some kind of decision support system? But since let's say like we have users that located in a different place, so the way that we connect the users, the way we use some kind of web base. So I'm thinking that would that be possible using any logistic as the engine behind, like, okay, we have an interface just to enable the users to put the inputs for the optimization, and then the any logistic do the optimization, and then the users can do some experimentation because the result from the optimization can shoot back to the users through the website. So I'm thinking, yeah. So would it be possible for any logistic to do that?
Yes, there are two options. Any logistics can be used as a solver behind your website, so that the data are transferred to any logistics database. It runs the optimization and provides back result, which is again which is written to a database, and then website shows this result from a database. And the second option will be available later because it's under construction at the moment. It's a new version of any logistics, which is browser based. So in that case, it will be possible to have a backend service of any logistics installed somewhere, and users could access it through their browsers.
Okay. Thank you.
So yes, the answer is yes, but it depends on the actual implementation, how to do that. And the second question is from Krishna.
Okay, this is more on the security and asking if there is a certification or license for application. I guess he's talking or she's talking about data. ICT and so logistics, are they secure, reliable? Yeah.
Yes. So this software is installed on a local workstation, and it doesn't transfer any data somewhere. So it uses latitudes and longitudes to download routes and distances, but it doesn't transfer any namings, any values outside of the local machine. So everything, the data itself and the optimization are on a local machine. So the security questions are the same, or security of data in any logistics depends on security of the local machine where it is installed. So if it's protected with password and firewall, then it's the same level of